Hi, the next section, 5.6, the paired t-test. So in previous sections, the 5.3 and 5.5, that we compare the sample X and Y, but these samples are not corresponding each other at observation level. So we have X1 to Xn, Y1 to Ym, but no individual corresponding. But here in the paired test, we have the exact correspondence between observations. X1 corresponds to Y1, X2 corresponds to Y2, and so on. So that we can say that we have the individuals 1 to n, and within each individual that we have two observations, X1 and X2. In such a case, that we can do the paired t-test, that is done two sample t-tests or two sample Wilcoxon tests with this condition. So remember, the important thing is that the two sample t-test may be appropriate even if the two samples have the same size. But the paired t-test is appropriate if we have correspondence between observations. Yep. And example, so we want to compare the two different tires and which tire wear more than the other. And since different cars have the different wear of tire because of weight or driver or the location. So we install these two types of tire on the same cars. So tire A on somewhere, maybe randomly, maybe rear left tire or right front tire, just randomly assign the tire A to these 5 automobiles, and tire B also on the same 5 automobiles. Then you can see the data. So tire A and tire B, we have large variability. For example, the tire A, wear of tire A ranges from 8.8 to 12.3. So range is the 3.5. And the tire B also have the range of 3.5. So it's pretty wide variability. But we think about the difference between these two observations. The difference is almost consistently positive. So that means tire A, the wears more than the tire B consistently. So if you do two sample t-test, we cannot detect the difference between A and B probably, because difference is, okay, so 0.48, but the standard deviations are very large. But if we take the difference first, the difference is the same. So the average is 0.48. So this is exactly the difference between X1 bar and X2 bar. But standard deviation is much smaller because a kind of noise cancel within each individual car. So as a result, that we can detect the significance, and we will see how to implement this in R. So at first, define tire A and tire B, two data sets and two variables. Then we can do the t-dot test of A minus B. So at first, take the difference between A minus B and just put it in t-dot test. Then it will do one sample t-test. So we can get the t value. So this was d bar divided by SB. Then degrees of freedom, that is 5 minus 1, then p-value. So this is very significant. Reject null hypothesis that the wear of tire A is equal to the wear of tire B. And we can do the same thing as different code here. T-dot test A, B, paired equals true. So this will do the same test as this code. And the Wilcoxon test, the same thing. So if we have the two samples, x1 and y1, and x1 to xn and y1 to yn, so these are corresponding each other, then take difference, then d1 to dn. So if d1 distribution of d is not normally distributed, so distribution of this is not normal, that we can apply the Wilcoxon, one sample Wilcoxon test, one sample Wilcoxon signed rank test in section 5.2. Signed rank test. So the procedure is just the same as 5.2. So we omit an example. So this is another way to test paired samples.